All right, so let's take a look at this picture now and compare the left side to the right side. Well, on the left side and the right side, we have the same number of neutrons and protons. But on the right-hand side, we have an alpha particle shooting out. And so if we look at that, right, as soon as the nucleus just splits apart a little bit, the electromagnetic repulsion just takes over and then they split apart really rapidly, right? Because the strong force, the strong nuclear force doesn't act over a very long range at all, very small range, right? So these subsequent nuclei, the helium nucleus, which is the alpha particle here, will split apart from the original nucleus very rapidly, and they'll split apart. So let's take a look at what happens then with the energy, because we know that the nucleons apart are different than together. Here's radium to radon, so we have radium 226 and then radon. And and then an alpha particle shoots out. And so what we want to do is we want to find the difference in mass before and after, and then that will be the kinetic energy given to the particles after the decay. Because remember, as mass and energy equivalence here, right? Because you can't just separate one from the other. We're going to get a difference in mass here. The radium together is going to be a different mass than adding these two up, because you're going to have some energy left over afterwards, and that's going to be given to the particles. Now, here's an important note here. As long as the electrons are there before and after, you can actually leave the full atomic mass. You don't have to subtract the electron mass from any of these. The helium nucleus obviously won't have any, but radon will, right? We'll have the electrons there. So yeah, you can just leave the electrons there. So so what we can do then is we can take a look at the mass before, which is 226.0254 U. We can get the difference in mass. Afterwards, it's radon plus helium. And we can get the mass defect. We'll subtract the two. So this is the difference in mass before and after. Therefore, if we get that mass in kilograms and we use E equals mc squared, that energy will come out to be this, and that is the kinetic energy of the particles. So in other words, you have that radium just sitting there. When an alpha decays, the radon and the alpha particle have this much energy as they split apart, and they're moving. They have a kinetic energy, right? And so that mass that's lost is turned into energy, and it splits apart, and those particles move apart. So another thing that we can look at is conservation of momentum. And remember, looking at the relative velocity, how could we determine the relative velocity of these particles after they split apart? So here's the radium atom just sitting there, the nucleus, and then it decays into radon, shooting up like this, and the alpha particle, right? So remember, with conservation momentum, all initial momentum must equal all final momentum. So if the initial momentum is 0, the final must be 0, right? So you remember, with a cannon has a lot more mass than that little cannonball. So the recoil of the cannon is going to be much less than the velocity of that cannonball, and therefore we can get a relative amount. So if we do that, we know conservation momentum, m1v1 initial plus m2v2 initial equals m1v1 final, m2v2 final. They're all together starting out, and they're both 0, right? The radon and the alpha particle beforehand. When it shoots out the alpha particle, we have our values here, mass 1, v1, and if we say that's going, up the page to the positive y up here, then we've got that. And then the other particle is negative, some negative velocity, and we can do that. So if we set up a ratio, we can add this to the other side. We'll set up a ratio, and what we get is that the velocity 1 is going to be 4/220 of the speed of the other one. Or in other words, the other one's going to be this much faster. The rate alpha particle is going to be 222 divided by 4 times faster. And so this gives us the relative amount, right? this is a fraction of what it would be, and then the velocity of the alpha particle is going to be much, much greater. And then again, that's because of mass. So if there's less mass afterwards, if there's missing mass, then energy was released. And so, if we take a look at this one here, the mass before was 226.0254, and then the mass after was 226.0191. Yeah, and so we have a mass defect of 0.0063, and there's energy released there. But if there is more energy, if there is more mass after the reaction, then it will actually take energy to make that reaction occur. And so you have to introduce energy to be able to make that happen. So up to this point, we've looked at natural transmutations where, the afterward effect, we're looking at, a missing mass, that's the energy released. And artificial transmutations occur when it's induced or caused by something outside the nucleus. And so we'll take a look at that now. So here's an artificial transmutation. This is nitrogen that is bombarded with an alpha particle, and therefore the nucleus becomes oxygen plus a proton. And so in this one here, it's going to take energy to make this happen. And we can look at that here. So we have our values for nitrogen, for oxygen, for helium, for a proton here. And yeah, let's go ahead and evaluate that. So we want to find the mass before and after. So, and then again, the missing mass before must be the kinetic energy of the alpha particle to make the reaction occur. And yeah, we can find what energy for the alpha particle would be required for this reaction. So the mass before, we add up the nitrogen plus the alpha particle, the helium nucleus, 4.0026, and we get that value there. And when we find the difference in mass, the mass afterwards is the oxygen plus the proton, and we've got that. And so the mass defect is 0.00073335 U. And if you notice with the masses, right, the mass after is greater than before. Before it's this much mass, after it's this much. So this will not naturally occur. You have to force this. And so, yeah, we can figure out how much energy it takes. We convert our mass to kilograms, equals mc squared. And it's going to take 1.096 times 10 to the negative 13th joules to make this reaction occur. All right, so fission occurs when unstable nuclei splits apart into two lighter nuclei, forming two elements. And we have a good simulation here. This is uranium-235 that has a neutron come into it and breaks up into two smaller nuclei, and neutrons are released. So fission occurs, happens when the nuclei is unstable and it splits apart. Now, if you remember with the strong nuclear force, as soon as the nucleus just starts to get apart, they're going to separate out rapidly. And this one doesn't show that as much. The krypton and barium don't split apart as rapidly, spreading apart. But yeah, those two nuclei are going to split apart and separate out, and in this case, more neutrons are going to be released. Mass is destroyed, producing energy according to equals mc squared, and yeah, and we see that. And I encourage you to go to PhET and go to nuclear fission. You could even Google search PhET nuclear fission and play with that simulation. There's some great stuff in there. You can do the one where you shoot a neutron towards uranium-235 nucleus, see what happens with the stability, and then you can also play with the nuclear reactor and see how that works in terms of speeding up or slowing down the nuclear fission reaction in a reactor. All right, so in nuclear fission, we have a neutron entering a uranium-235 nucleus, and it becomes uranium-236. And
it becomes unstable, actually very unstable very quick, very small half-life, and it will split into lighter nuclei. It becomes barium and krypton, and plus will also eject 3 neutrons. And so the energy released here is significant, and we're going to look at that now. And this is the nuclear fission responsible for how we have our nuclear reactors, and also this was used in nuclear weaponry. All right, so the mass difference will give us the kinetic energy of the products, right? So same deal here. The mass before, we have uranium plus a neutron there. So our total mass before is 236.0526, and actually we should say here this is the mass of the uranium-236 here. The mass afterwards is adding up the barium, adding up the krypton, and the 3 neutrons, and we get our mass defect. The difference in mass here is 0.185875 and we can get this into kilograms, equals mc squared. And yeah, this is the energy that's released. And if we get this into electron volts, it makes a little bit more intuitive sense. And we've got 173.6 mega electron volts that's released. Now again, this is just for one nuclear fission, where the nucleus splits apart, the barium and krypton and the 3 neutrons split out and have that energy. And so as they fly apart, that energy can be harnessed and used, and so that's what we're moving into now. So neutron-induced fission is artificial transmutation, and neutron-induced fission produces a chain reaction. And so you probably heard that word chain reaction before, and we discussed this in class. Nuclear power plants operate on the harnessing the energy released in fission by controlling a chain reaction. And in that simulation that I mentioned earlier in PhET, you can see that chain reaction pretty clearly in one of those simulations where, yeah, you've got enough uranium-235 in there so that the reaction can continue. Because if one of those uranium-235s becomes 236, and it splits up into barium and krypton, and 3 neutrons go out, those neutrons can enter in subsequent uranium-235s, and when that happens, can create more fissions, and then more fissions, and then more fissions, and that's the chain reaction. And nuclear weapons, as compared to power plants, depend on the uncontrolled fission reaction as compared to a controlled. So in a nuclear power plant, we can move those control rods up and down, we can control that. In a nuclear weapon, the design is to have the uranium-235 so refined so that it's pretty much only 235. You start the chain reaction and it's uncontrolled, and it just rapidly happens there. Yeah, why does a neutron have to be used? Well, when we take a look at the chain reaction, the uranium-235 has to become 236, and that's what we see there. Now, for the nuclear chain reaction, you must have a critical mass. It's called a critical mass. It's the minimum of substance to have a chain reaction. Uranium-235, can be found around, but it's mixed around. We have a lot of other types of uranium isotopes. The little vial that I have in class for the uranium from Casper, Wyoming, has a whole mix of different types of uranium in there, and you have to isolate out the uranium-235 to get nuclear fuel, and you have to have enough of that refined because, as you can see in the simulation, if you pull that up, and you have uranium-235 and 238, if you have too many 238s in there, it's just going to absorb the neutron. It's going to become uranium-239. It's just going to sit there. And so you have to have enough of the refined uranium to have the chain reaction. Now, fusion, on the other hand, is where you have 2 nuclei coming together to form a new element. And fusion is the most energetic of all nuclear reactions. It's the energy produced by the sun, and the fusion of these light elements become heavier elements, and yeah, and lots of energy is released. And so you can see the simulation here, and we have the fusion happening where we have the nuclei coming together and forming a heavier nucleus, and energy is released in that. And so that's what we're going to take a look at now. So again, fusion is the energy that is produced by the sun, and we're trying very hard to try to do this on Earth, to be able to control this, be able to get energy from it. It's very hard to control. You have to have extremely high temperatures, and up to this point, it takes more energy putting into the system than we actually get out of it. And so that's what we're dealing with right now. The nice thing is that you don't have the radioactive waste products. And so, you know, with fission, we have krypton and barium, which are nasty, you know, byproducts and, you know, continue to decay. And so we have to be very careful with those. We have to isolate those and you know, take that nuclear waste and, you know, make sure it's not going to be exposed to people. What's great with fusion though, rather, is that it, yeah, you don't have the hazardous waste products, and it's very safe. And you can shut it down very quickly as well. You just, you know, if we were trying to control it, you just, you know, don't add any more of the elements there, and then it shuts down. There's no chance for a nuclear meltdown like we have with fission. Now, it's very hard to make fusion happen because there's electrostatic repulsion. If you think about it, right, what you're trying to do is get these nuclei to come together, and they definitely don't want to come together. If you have, let's say, these two elements here, you know, trying to come together, that electrostatic repulsion is extremely strong. You know, and remember, the strong nuclear force only acts once they get, you know, really close. And so to be able to get those together, you have to have very high temperatures and to make that happen. Now, once they do fuse together, they release a lot of energy. One of the, you know, research and engineering projects going on is ITER, and you can look that up online. We also have research here in the U.S. with the ignition facility, and even private organizations like Lockheed Martin are trying to do this. It would revolutionize energy if we could, you know, be able to, you know, create a fusion reaction that's controlled and we could get energy from it. It would solve all our energy problems, no problem. It's just very, very hard to make that successful, but we're working hard to do that.